afternoon, good evening, wherever you are around the world. Thank you for joining us today. We have a very exciting webinar, our LoRA Bake-Off, coming on the heels of a webinar we had a few weeks ago where we introduced Loraland, in which we fine-tuned 25 plus adapters on Mistral to demonstrate how they can rival and actually outperform GPT-4 in almost all cases. We've now actually, our team of experts has fine-tuned many, many more models and is going to share with you all today our findings and guidance so you can go replicate these results and create your own results and learn more about when fine-tuning makes the most sense, what models are performing the best, and all that good stuff. So let's jump in. A few small logistics reminders. The lines are muted, but that doesn't mean we don't want it to be interactive. We do want it to be interactive. So please put your questions in chat. Both our speakers and we have other folks from Predibase who will be online who can answer some of your questions. And we will have a live interactive Q&A session at the end where we'll go back through and try to address as many questions as possible. So please put your questions in chat. As we're getting started this morning, we have a few polls for folks. Take part in our polls. We're trying to learn more about where people are on their journey with LLMs and also wait for you to share with your peers where you're at because you can see the results. And we have a couple handouts for folks too. We have our definitive guide to fine tuning you can download as well as the slides from today's session. And of course, we encourage you to try out Predibase if you're interested. We offer $25 in free credits so you can fine tune and serve many popular open source models like the Llama series, Zephyr, Mistral, all that fun stuff. So if you want to try it out, you can go to our website or use that short link right there. And now moving on to introducing our speakers briefly. We have our dynamic duo from our machine learning engineering team who have done a lot of the development around our platform as it relates to the fine-tuning experience, but also fine-tune hundreds of models, both at Predibase and sort of previous lives as well. I can't think of a better team to sort of educate everyone today about best practice about fine-tuning and share insights. So we have Justin and Tim joining us. Very excited for them to take you guys through our insights today. So with that, I'll hand it over to Tim.
Thanks, Michael. Hey guys, so today we're here to just discuss a little bit more about our results post Loraland. Loraland was a launch that we did a few weeks ago to show just the power of fine-tuning when we showed 25 adapters all fine-tuned to beat GPT-4 on a variety of tasks. So here, Loraland was the results of hard work across all of the teams here at Predibase, and so all of the fruits of our efforts were shown in our last webinar. It was a playground in which you can explore these 25 Mistral 7 billion adapters that we fine-tuned. And like I said before, the performances at minimum rivaled that of GPT-4 on the tasks that they were trained for. And so a little bit more detail on what Loraland was intended to do. In this work, we aim to demonstrate, first of all, that smaller fine-tuned models could consistently outperform larger generalist models. And while this isn't really new, the first demonstration of this, I think, was probably around 2014. It's a point that's really worth reiterating, especially as we start seeing these very large models of GPT-4 come out. It was also to demonstrate the broad flexibility of specializing many, many models using the same base model, using a technique called parameter-efficient fine-tuning, also called QLoRA. We also wanted to put our money where our mouth is and just show that we can do this really fast, light performance production application that serves a lot of these specialized models with a real-world workload, as well as real-world traffic. And then finally, we wanted to show that we could serve all of these 25 LLMs on a single GPU using LoRAX, which is a technology that takes advantage of PEF mechanics to efficiently load multiple sets of adapter weights at the same time. So to show, we were very, very happy with how the launch went. After we launched, we made it to the top page of Reddit, and we were also retweeted by Yan LeCun, which is super, super cool to see. But we wanted to go further after our Loraland results. And so I posed to you the question, how many engineers does it take to change a light bulb? And I can tell you confidently that we don't know. But it only takes one to fine-tune and evaluate 700 adapters. Our technical work for Loraland effectively unlocked our ability to quickly train and evaluate adapters on a scale that we just had not done before. I'll be going into this a little bit more deeply later on in the presentation, but we did some technical work that allowed us to really quickly train and evaluate our adapters. And this accelerated tempo motivated us to greatly expand upon our experiments by evaluating adapters for 10 different base models on over 30 datasets. And with all of the trials that we did, this ended up being over 700 adapters that we fine-tuned and evaluated. To take a quick step back, I'm going to do a brief introduction to what adapters are. As a general introduction, an adapter is a small set of trained model weights produced during fine-tuning used to specialize a pre-trained base model. So in the world of LLM fine-tuning, we have this dichotomy between what we would consider to be traditional fine-tuning and then something called parameter-efficient fine-tuning. So in this traditional fine-tuning space, we would have our data sets and we would update all of the parameters in our LLM, whether that be 2 billion, 7 billion, 70 billion parameters. But unfortunately, this is very expensive, both memory-wise and runtime-wise. Just simply because we have all these parameters that we need to keep track of updates for and then update as well. The alternative effectively takes new weights that form a very small proportion of the entire model, so usually around 1% of the model weights, and we fine-tune those new weights instead of the entire model. The result is that we have this frozen base model and this set of new fine-tuned weights that what we call an adapter. To give a little bit more of a visual representation of what this is, one of the most popular adapters out there right now is what we call a low-rank adaptation, or LoRA. We, like I said, freeze the LLM's original weights, and then we insert new ones. We have two new adapters in this paradigm. We have these A and B tensors that can be effectively thought of as projection matrices to and from a low dimensional space. You keep the pre-training weights completely frozen, and during backpropagation, you just only update these two new tensors. So as you can see, it's a lot more efficient to fine-tune using PEFT, but there is another trick that we can apply to further optimize performance. And this is what we call QLoRA, which is using 4-bit quantization to further optimize our performance. We store all the model parameters in 4-bit, and then on an as-needed basis, we dequantize these parameters to brain float 16 to perform computations in both our forward and our backward passes. And because these weights are dequantized, like I said, using an as-needed basis, memory usage stays low during training and during inference. With that out of the way, I'm going to present a little bit of the methodology as to how we did this LoRA bake-off, as well as a little bit of methodology on the original Loraland launch. So with the original Loraland launch, we selected our data sets from ones that were widely available and either commonly used for benchmarking or as this proxy for industry tasks. These data sets that fell in the latter category of industry tasks included things like content moderation or SQL generation or sentiment analysis. The common benchmarking data sets, the ones that are often seen in research, included ConL++ for named entity recognition. We have some of these glue data sets like QQP for question comparison, and many others that we did. You can see on the screen here this academic benchmarks section. And then, as you can see as well, the tasks that we chose spanned classical text generation to some more structured output and classification tasks. The length of the input text that we chose varied pretty substantially across these tasks. So we had some fairly short text, and we had some really long documents that we had to process. Furthermore, a lot of these data sets had this very long tail distribution. So there are a small number of examples that have significantly longer sequences than the mean. And to balance between accommodating these longer sequences and maintaining computational efficiency, we opted to train our models using P95 percentile of the maximum text length, effectively just removing the longest samples from our data set when we fine-tuned. Next, during prompt selection, we wanted to make sure that our prompts would be fair, even if presented to a non-fine-tuned model, whether that be GPT-3.5, GPT-4, or simply one of the base models that we didn't apply an adapter to. This is to make sure that our evaluations would be as fair as possible. And so some of the tactics that we tried to do were we specified what the output type would be. So sometimes that would be, we specified JSON outputs to make sure that even a base model would be prompted correctly. We would do single shot prompting for some of our more technically difficult questions or some of our more complicated questions, just to make sure that the model had a sense of what the output format should be. We also used specific delineators and clearly prompted the model at the end of our prompts to make sure the model had no confusion as to what it was supposed to be doing. And then finally, some of the other parameters that we chose are listed on the screen here. 4-bit quantization and LoRA rank 8 are the Predibase defaults that we set for fine-tuning. These are the ones that we stuck with for Loraland to begin with. And due to the solid results that Loraland gave, we stuck with them for the bake-off. The biggest change to our parameters, however, was going from 3 epochs, as we did for Loraland, to 40,000 training steps that we did for the bake-off. And we effectively had 2 reasons for doing so. The first was that some of our largest training jobs would take a considerable amount of time to run just due to the sheer size of the data sets. So we observed during the Loraland experiments that training loss generally converged well within the first 40,000 training steps. So we felt pretty comfortable limiting these larger data sets to 40,000 training steps to expedite the fine-tuning process. Furthermore, due to the different data set sizes, we felt that setting 40,000 training steps would be more consistent than setting 3 epochs because it ensures that each model sees the same number of data points, even if some of those data points are repeated. As for the evaluation metrics that we used, this is how we determine the strength of our adapters, so we had to be fairly careful in choosing them. The primary metrics that we used were accuracy for our classification tasks and rouge for our generation tasks. These are very common metrics across many of our LLM benchmarks. However, to ensure fairness, we applied a little bit of flexibility to these metrics, specifically in how they interpreted outputs. For instance, yes or no versus 0 and 1 versus true and false. If a model were to output true when we're looking for the answer yes, we tended to accept those as the same. This generally heavily benefited the base models rather than our adapters, as our adapters were generally able to adapt to a specific output format. Other metrics that we used included human eval for our code generation datasets, as well as a specific regex extraction method for GSM-8K, which is grade school math solving. Due to the verbose nature of some of the answers, we had to perform some extraction to correctly assess the accuracy of our models when doing so. Now, for the bake-off itself, you might be wondering how exactly did we train so many models so quickly with only one person? We created 2 harnesses to greatly accelerate our pace. One is a training harness, and the other is an evaluation harness. The training harness used the Predibase SDK to quickly launch a large number of training jobs by leveraging a task-level organization for our experiments. This task-level organization was designed to ensure consistency across our training and our evaluation runs. So what we did was we created a metadata file for each of our fine-tuning tasks. So each task could be, for instance, TLDR news summarization, or like GSMK, as I mentioned earlier. Each of these metadata files contained metadata like the prompt template that we used, the output column of the data set, the path to the data set locally, effectively just encompassing all of the data set specific information that was relevant to training and evaluation. What this allowed us to do is to standardize all other aspects of our training and evaluation flows. So we can just quickly iterate over the metadata of each task and swap them out while keeping all other parameters the same, so that only the dataset specific parameters were changed between training runs. This allowed for a much faster iteration cycle, as well as a much more consistent one. The evaluation harness, in my opinion, is a little bit more of the exciting one. The evaluation harness primarily consisted of 3 separate tools. First, we had the request generator, which is what we used to create JSON payloads that we would pass on to the parallel processor, which is the second of these tools. The parallel processor took our JSON payloads and passed them off to a REST API. In our case, for Loraland, we hit both the Predibase API as well as the OpenAI API, just so we could evaluate against GPT-4. And then for the LoRA bake-off, we just consistently hit the Predibase API to evaluate all of these 700 adapters that we trained. Finally, it takes these results and it processes them and puts them into the last tool, which is the response parser, which is what applied our metric functions to the responses. This combination of these two harnesses is what enabled the completion of approximately 300 training jobs and their evaluations in less than 24 hours, making our work much, much simpler, in that we could collect all of our results for 700 plus adapters in about 2 days. However, probably the most exciting thing for you guys is that we have now made our evaluation harness public. So you can test this out for yourself on your own adapters that you've trained with Predibase and evaluate their performance for yourself. And right now, I'm going to switch over to giving you guys a quick demo of just how this works. So I'm going to stop sharing my screen here. And I'm going to switch over here real quick. So as you can see, this is just empty so far. I'm going to do a quick pull. So as you can see, the name of this repo is going to be Predibase/LoRA Bakeoff. And that's just going to clone this repository over here. I'm going to start by showing you guys what our metadata files look like. So in this metadata.yaml file, you can see that we provide dataset names, dataset description. These aren't strictly necessary, but are good for us just to have an organizational sense. The really key ones here that you want to take a look at are the metric name, which is exactly what it sounds like. This is the metric function that we have specified. This is going to be listed in our metric functions.py file. Can we increase the font size? Let me see if I can just, is this better for you guys? Let me go in one more. Better? Cool. So, like I said, here we have the metric name. This is effectively just the metric function that we would specify. So in our case, this is what we call binary accuracy flex. So this is what I was mentioning before, 0 or 1, yes or no, true or false. These are all treated as effectively the same answer. We have our split column value, which is accidentally duplicated here, but split column determines what's the name of the column that defines our splits. The split column value specifies which split we want to use. And then data path points to the local path of our data sets. So in this case, it is this data set here. This SST2 data set effectively just determines whether these, let me explain here that the split column is what we said before. Split is determined as 0, 1, or 2. 0 is our training set, 1 is our validation set, and 2 is our test set. We have this sentence column here that we would pass into our prompt template. If you go back to the metadata.yaml file, we have this prompt template that states the sentence. So this sentence would be formatted into this prompt template. And then we have the label, which is just the sentiment value. And this index column is just helps for us to make sure that all of our keys are aligned properly. Cool. And then now to show you what the script looks like. This is, again, the 3 components of our harness. We have the request generator, we have the parallel processor, and we have the response parser. We specify an output directory. We specify which task to use, which is what references this name here, glue SST2 in our task directory. We specify how many examples we want to evaluate on. This is the cap. And we specify how many maxi tokens we want. This adapter ID specifies which adapter we're using in the Predibase environment. and that's our request generator. So if I'm going to now specify what my token is, so I'm going to go into my .m file over here, and I'm going to swap out this API token for one that I have here from our demo. And I'm going to run this request generator. And so now in this results subdirectory, I have our requests. So this is the JSON format that's the Predibase REST API will take in. And so we have here information like our API token that we just set, the adapter source, the adapter ID, so on and so forth. Next, we're going to pass in this request file and run the parallel processor. And this kicks off all of our requests. So you will see some failures here, but we have our retry logic that allows us to keep running this. And so as this runs, this is just going to parallelize all of our requests, send them over to the Predibase API, and we're going to get our responses back in this file here. And so you'll see that we have our generated text, as well as this df index here, which maps each of these responses back to the original database, to the original data set, so that when we do our metric function calling, everything is lined up properly with the right label, which is what I'll show now. We run this response parser, and it'll just iterate over all of our responses and outputs our binary accuracy, which in this case is about 95%. And that's basically it. So with this, all you need to do is you provide a task metadata YAML file, you pass in your data sets, and you pass in a Predibase API token into your .m file, and you're able to just run these scripts and hit our backend to just get your responses back very, very quickly. And so now I'll just stop sharing this and switch back to slides. Cool. And now I hand things over to Justin to discuss our results and findings.
Hello, can you guys hear me? You guys hear and see me?
Yep, I think you're good.
Okay, thanks, Tim. All right, so yeah, as Tim demonstrated, we have this training and evaluation harness powered by the Predibase SDK and the Predibase REST API that allows us to issue a bunch of training jobs at once. And then basically once those jobs complete, we use the REST-based evaluation harness to gather all of the generated outputs we need. We implement a quick metric function, and we get some metric values that are pretty easy to parse out. Next slide. So that kind of was a big impetus for this. We were like, what can we do with this harness? And so that's what led to this big LoRA bake-off. And specifically in the context of adapter-based fine-tuning, we wanted to compare the most popular open source based models out there from the big tech companies like Microsoft, Google, Meta, as well as the other startups out there like Mistral and Hugging Face. And then, for all of these base models, we're sticking with these 29 tasks that span the classic NLP problems, coding, question answering, reasoning, and math. And then finally, we want to be able to interpret those metrics for the fine-tuned models by comparing them to all of the base models before and after fine-tuning, as well as GPT 3.5 or ChatGPT and GPT-4. And with all systems across all these tasks, we want to be very consistent with using the same prompt. Next slide. So as Tim mentioned, these are the parameters that we are using: 4-bit quantization, 8 for the LoRa ring, 40K training examples. And I just want to call out that we were very intentional about not doing any hyperparameter tuning. These are the basic parameters that you get out of the box when you use Predibase. And yeah, we just imagine there's also so many models, we don't even have the time to really do that hyperparameter tuning. So sticking with these very coarse defaults across the board. Next slide. Okay, so here's a graph with all of our results, and that's it. No, I'm just kidding. We definitely need to dive into the numbers into more detail, but I just wanted to highlight that this is the default graph that Google Sheets generates when you insert a chart with that full matrix of 290 adapters. In this form, it's definitely difficult to interpret, but it's certainly pretty to look at. Cool. So our highest level observation is that when it comes to performance on specialized tasks, adapter-based fine-tuning is indeed superior to GPT-4. And for the bake-off, we selected these 10 base models. And we did that, we chose these models because they're very recognizable in the industry. They're quite popular, and their benchmarks are also widely published in papers and so forth. And so you'll notice that we limited our base model selection to just ones that were 7 billion parameters or less. And the reason for this is twofold. One, for the bake-off, we were signing ourselves up to train this very high volume of models. And so we wanted to make sure that each model can just be trained on a single A10G. And then the second is that the theory is that for many specialized tasks, they're intrinsically low rank. And so these pre-trained base models, even just 7 billion parameters, there's already a ton of information in them. And for many tasks, 7 billion is already bigger than they really need to be. And then the line in green, the adapter is trained on top of Mistral 7 billion base. That is what is being served in the Loraland website today. Cool. So before doing any fine-tuning using our task prompts, this is a table showing how all the base models perform out of the box. Each row in the table corresponds to a task, and the base models are laid out across the columns. And across the board, we see that OpenAI, when it comes to base models out of the box without any fine-tuning, it's definitely the top performer in most rows. So that the green cell is highlighting the best results per row, and we see that the right side, which is the OpenAI models, they get the most green cells. So instead of looking at the top performer, we can also do something where we average the performance over all tasks. And if we do that, then we reach the same conclusion. So GPT-4 is clearly the best model out of the box. Now let's fold in fine-tuning into the equation. So in this table, we see that each cell now has 2 numbers in it. One is for the performance of the fine-tuned adapter, and the number in parentheses is the lift over the base model. And at a quick glance, you should notice that a lot of the numbers are significantly better. There's a lot of plus signs all around. And don't worry about trying to read all these numbers in detail. We have other graphs to show you as well. So the first insight is that there is a consistent and significant boost from fine-tuning. Overall, we see kind of like the worse that the worse that the base model is, the more headroom there is for there to have a measurable boost. So that's why we see kind of Gemma 2 billion taking the top spot here for getting the biggest boost from fine-tuning. Overall, we see anywhere between 23 to 50 points of improvement on average. And again, this is just with the default fine-tuning parameters on Predibase. If we were to use other, fine-tuning parameters, we may see even higher boosts. Here's another depiction of the average boost from fine-tuning, shown in red, combined with what the base model is able to get, which is in blue. And here, the models are listed from left to right, from worst to best. with the combined performance. And we see that the fine-tuned models are better than GPT-4 for the most part. GPT-4 is, taking this middle spot here. We see that all fine-tuned models were better than GPT 3.5, and all 7 billion fine-tuned models were better than GPT-4, with the notable exception of Gemma 7 billion instruct. Cool. If we zoom into kind of the bottom 5 here, the bottom 5 open source models, performance appears to be stratified by vanilla model versus instruction tuned rather than by model size. Particularly of note is that the 4 Gemma models were at the very bottom of the base models, beaten even by Phi2. Gemma 2 billion instruct, despite being the smaller model, it actually surpasses Gemma 7 billion instruct after fine-tuning. But both models are still doing worse than GPT-4's performance on average. Cool. We're speculating that this is possibly due to some bugs with the Gemma models as identified by Unsloth, I think last week. Cool. And also of note is that, if you go back to so we also want to note that all 3 of the 2 billion parameter models are in the bottom 5. So that's interesting to see that smaller is worse and bigger is better. All right, next. In the top 5, the results are pretty in line with expectations. We see that the Mistral architecture seems to kind of take the cake here, where Llama is definitely a little bit lower than Mistral, and that's even a little bit lower than Zephyr. But of note, Zephyr is a base model published by Hugging Face, but it's actually based on the Mistral model. Cool. We can also examine base models by how often they were able to produce a top performing adapter. And here we see that Mistral 7 billion produced the most number of top performing adapters on 8 out of the 29 tasks. So then to answer this question of which base model is the best for adapter-based fine-tuning, the top level answer is that it depends on your task. But if we want to do this kind of big average type of exercise, there's kind of 2 ways to answer this question. Mistral 7 billion is the best base model for training adapters by number of instances of producing a top performing adapter, followed by Zephyr. But Zephyr actually takes the top spot for the best overall average. Cool. So now if we go back to this graph, next slide. We also see some interesting differences between the fine-tuning of vanilla-based models versus fine-tuning the models that were previously instruction-tuned. And so here, counterintuitively, we find that at least for this set of training parameters and tasks, the non-instruction-tuned models produce better adapters. But we speculate that this could be due to the fact that the non-instruction-tuned models start out less overfit to any prompt-specific tags. And therefore, when we are trying to fine-tune them with our coarse prompts that may or may not have those tags, actually, they don't have those tags, the loss can be optimized more quickly. On the 2 billion parameter playing fields, we see that Gemma instruct was better than Phi out of the box. You see that Gemma's blue bar is higher than Phi's blue bar. However, after fine-tuning, we see that Phi models were better across the board. Cool. All right, so we've talked about averages this whole time, and looking at averages is certainly useful to get these kinds of high-level observations. However, I also want to call out that on a per-task basis, we do see that in 5 of the 29 tasks, GPT-4 is still better than kind of the best fine-tuned adapter. So why is it that for some tasks, the fine-tuned models weren't better than GPT-4? And so here we see a kind of rough categorization of the different types of tasks that we fine-tuned on. On the left, we have classification going to coding. And kind of our speculation is that the narrower the task is, the more the performance improves through fine-tuning. The loss curves are sharper, and it's also more likely that the adapter outperforms GPT-4. And then conversely, for broader tasks like coding in Python, we think of it as coding, but it's actually quite a broad task because there's many different types of questions that could be asked in terms of a coding domain. But that is where we see our fine-tuned adapters, at least trained with rank 8 and 40,000 training steps. They are not doing as good as GPT-4. So in terms of what we can do to improve adapters from here, I think there's two main areas of investment that I see that we did not explore in the bake-off. So first is to actually iterate on the hyperparameters. We're using the default parameters out of the box, and we explicitly did no hyperparameter tuning. But all things considered, this is a very it's intended to just be a start for our model. So using 4-bit quantization, maybe like a higher level of precision will be better for the more broader tasks. The rank of 8 is actually relatively small. The original LoRA paper experimented between, I think 4 and 256. And so increasing that rank will increase the level of precision in terms of how weights get applied to the pre-trained models. And then finally, we only trained for 40,000 training steps. And so, and this was actually a bump up from a previous round of experiments where we just trained for 20,000 training steps. And from 20,000 to 40,000, we observed like a big boost across the board. So I think if we boost this to be even further up, I think we'll see improvements there as well. 40,000 training steps, by the way, just to give you a sense of it, is with batch size 1, it's 40,000 training examples. And for some of these tasks, that's not even a full epoch. So that's to give you a frame of reference. And then the second idea for improving adapters is to explore other base models. So, our initial selection of 10 is based on what we thought was kind of popular, and we only looked at 7 billion parameter models. So one, we can definitely look at models that are larger. There's 13 billion, 70 billion parameters. And then finally, there's other specialized base models that are starting to come out now. So Code Llama was released by Meta not too long ago, as well as Orca Math from Microsoft. Code Llama specialized more for coding tests. Orca Math specialized more for mathematical question answering. And for both of them, I would expect to see, for coding and math respectively, stronger performances out of the box, as well as performance that gets better after you do adapter-based fine-tuning. Cool. So drilling into this question even more, there's this kind of open question about specialization and narrowness, right? And we wanted to see if we could observe anything and make a comment on that in our experiments. And so with all the models that we trained across this diversity of tasks, we wanted to see if we could spot any patterns. Specifically, can we predict the boost in quality of fine-tuning over the base model or over GPT-4 before running any empirical experiments and only looking at heuristics in dataset complexity? And so for the heuristics for dataset complexity, we have input sequence length, output sequence length, and then the example sequence length. So both input and output, you combine them together. Then we have input versus output Rouge L similarity score. And this comes from the self-instruct paper, where kind of you're measuring how different or similar the inputs and outputs are. Then we also looked at compressibility. This is like if you ever create like a zip file, the way that happens is that, you do string character, counting, for example, and you can reduce the size. So it's some measure of kind of like the more compressible the data set is, maybe the easier it is, or less complex it is. And then finally, the number of examples. And then on the model quality targets side, we're specifically trying to see if we can predict this average metric lift over the base model or an average metric lift over GPT-4. And so here is the full correlation matrix. this is a lot of numbers because we're using many different heuristics, but it turns out a lot of dataset complexity heuristics correlate with each other pretty strongly. Next slide. But when we look at correlations with respect to model lift and GPT-4 lift specifically, we actually see only moderately positive and moderately negative correlations. So moderate positive correlations for base models include input length average as well as input length standard deviation. I apologize for the table. The sigma symbol didn't get rendered, but yeah, it's mu is for the mean, and then the second entry is the standard deviation. So what does that mean in terms of positive correlations for base model lift? So it means that the longer and more varied the input lengths, the higher the lift that the fine-tuned adapter will get over the base model. And then for GPT-4 lift, we see some moderate negative correlations with output length mean and output length standard deviation. So basically that means the longer and more varied the output lengths, the outputs, the lower the lift that the fine-tuned adapter will get over GPT-4 performance. So I will say the correlations aren't super strong, but the observations are very consistent with our hypothesis that narrower, easier tasks are more likely to see success with fine-tuned adapters. Next slide. So if we train linear regression models to predict the lift of quality over base model in GPT-4, we find that actually we're able to get a decent mean absolute error of 6 to 10 points. So that's kind of cool to see. So in summary, does fine-tuning work? Yes. How consistent is fine-tuning? With basic training defaults in Predibase, we see that fine-tuning improves the base model almost 100% of the time. Fine-tuned models are better than GPT-4 for the most part. All fine-tuned models were better than GPT 3.5 on average score, and all 7 billion fine-tuned models were better than GPT-4, except for Gemma 7 billion instruct. What type of foundation model is better for training adapters? They're all kind of about the same, but we did see a slight, that non-instruction tuned models were slightly better for adapter-based fine-tuning, which is unintuitive, but we speculate it's due to prompt-specific tags. What is the best foundation model for training adapters, period? In this bake-off, we see that it's between Mistral 7 billion and Zephyr. Mistral 7 billion was best by number of instances of being the top performer. Zephyr was best by overall average. We find that bigger models are better. 2 billion models were consistently worse than 7 billion models, both with and without fine-tuning. And in the 2 billion parameter class, Gemma Instruct was better than Phi out of the box. However, after fine-tuning, Phi models were better on average. Math and coding continue to be the most challenging tasks for adapter-based fine-tuning. And finally, we find that dataset complexity does correlate with model quality, though the correlations are only moderate. And training a linear regression model to predict metric lift over the base model or over GPT-4 is actually only gets to 6 to 10 points of error. Nice. Cool. So we've trained all these specialized models, and we've shown that they're mostly better than GPT-4 in terms of quality. So that's pretty awesome. But what does it mean in terms of actual costs? So we've trained all these adapters, and we've analyzed them pretty rigorously to show that minimum effort for hyperparameter tuning, better than GPT-4, and it's very flexible for all these different tasks. Next slide. So that's where, to show the power of adapter-based fine-tuning, we just picked the 29 adapters that we get with the Mistral 7 billion parameter model. And then we actually wanted to get through the exercise of putting these models in production, which is the Loraland website that's up on predibase.com. And I wanted to talk about these costs for just a moment because, what is the meaning of adapter-based fine-tuning what does it mean for costs? So with Predibase, there are two costs that you incur when you choose to go with adapter-based fine-tuning of specialized models in your production application. The first is fine-tuning, and the second is model serving. For fine-tuning, Predibase charges a price per million tokens that depends on the size of the model. For Loraland, we trained all of our, those models are all trained on the same Mistral 7 billion base model, which comes out to 36 cents per million tokens. And with the default model configuration parameters, that comes out to about $8 per adapter. For serving costs, we are able to serve all 25 7 billion parameters on the Loraland website off of a single A100 GPU. So for those of you who don't know, a single GPU serving 25 LLMs is kind of unprecedented. So how did we actually do that? So in a traditional LLM deployment, you really just can fit one LLM on a GPU. So for 25 different LLMs, we would need a cluster of 25 GPUs. However, we are able to use this technology called LoRAX, and that's how we're able to serve them all on just one. To build some intuition for how LoRAX works, we can look at this coding metaphor. So if you imagine this, there's this code. This author is trying to define 4 classes: dog, bird, bear, and fish. And it looks like each class is defining a few methods. Is there anything wrong with this code? No. The code is perfectly functional, but the way it's written is actually really inefficient. And the reason is because 80% of the code is duplicated. All 4 of these class definitions are actually sharing the exact same 3 methods: init, eat, and sleep. So the way to make this more efficient is to define a single base class with all the common methods, and then you define the concise subclasses on top. And this results in a much more elegant and efficient representation because the duplicated code is just shared. So the tons of code that we needed separate dedicated files for, they all now fit into one neat Python file. So this idea of code reuse and polymorphism in software engineering is the same principle that we're applying to the 25 specialized LLMs that we're trying to serve. Here we see kind of 6 dedicated deployments for 6 different adapters. And for 25 models, of course, we would have 25 of these. And you'll notice that most of the parameters in light yellow, right, they're exactly the same because all 25 of these adapters are using the same Mistral 7 billion base model. And only a small portion of the weights, highlighted in red or blue, they vary from one adapter to another. So instead of each adapter having its own copy of the base model weights on GPU, we just have them all share the same base model weights on the same GPU. And so this is the key insight behind LoRAX, which allows us to do this efficient deployment of 25 LLMs on the same machine by loading all the adapters together, maintaining separate request queues for each of the adapters, and then that can be managed intelligently with a smart scheduling system. So coming back to costs, there's serverless and dedicated. Serverless is a pay-as-you-go option with low token-based pricing, no cold start time. And then traditional dedicated deployments, you can deploy one model per deployment, but then with LoRAX, Predibase, dedicated deployments enable you to serve multiple fine-tuned models on that same deployment, as long as all those models are using the same base model. So in terms of real production costs, we can kind of flash through this. So next slide. If we make some assumptions, this is kind of what the costs look like using dedicated deployments, one per adapter, or using GPT-4, they're extremely expensive. If we get rid of those costs and we wouldn't even consider those per month, that's just kind of crazy. Then we get this kind of clearer graph for all 25 adapters. But then you might be thinking, hold on, that's just an inference-only cost. What about the cost of fine-tuning? And so because it's only $8 to train each adapter. This was $7.85 to be exact for us. The all-in costs of training factored in, it's still cheaper. So the models are faster because they're smaller. They're still under budget, and they're also significantly better in terms of quality, as we saw. Next. The last thing to mention is that there is this trade-off between using Predibase's dedicated deployment option for your 25 adapters or just going with the serverless deployment. If we expanded LoRA Land, so right now LoRA Land is just 25 adapters. If we expand that to 64 or even 128 more adapters, then that's the moment where switching to a dedicated deployment would be more cost effective. So if we know that, so this is kind of a summary of kind of the costs here. So for the 25 LLMs that we did decide to put into production, we see that serverless is kind of the most cost-effective option at just $324 per month. And this is assuming 2 million tokens per month per adapter. And that's pretty reasonable. And that's what we have in production today. Cool. So just to wrap up with some final takeaways about our bake-off, I think LoRA Land continues to be this expression of a compelling blueprint for production AI deployments. So you start with some open source based model, and through fine-tuning, specifically parameter efficient fine-tuning, you're able to get models that are higher quality than what you would get from GPT-4 or GPT 3.5. And because they were trained with these PEFT kind of techniques, that allows us to deploy them with LoRAX, which is kind of the most effective, the most cost-effective solution for simultaneously deploying multiple models. All right, so some quick things to remember. Is fine-tuning worth it? With Predibase, we say absolutely. And next question, how many GPUs do we need for adapters? So because we're using the same base model, we just need one. If we were to deploy all 290 of the adapters that we trained with the bake-off experiments, then we would need one GPU per set of adapters. So, but still very, very efficient in terms of serving hardware. Cool. And then lastly, what is the future of AI? We believe that the future at Predibase is open source models and the LoRA Land results, the LoRA Land launch, as well as the bake-off kind of confirm our conviction in this. Cool. And that's all I have for you today.
All right. So we have a few minutes left. There was a lot of questions and the team was avidly answering them, but maybe start with like some more of the high level ones and we can drill in. If you just sum it up, like what's the benefit of, like if I have many tasks, right? What's the benefit of training one adapter per task versus using a large model?
Yeah, I guess I can tackle this question a bit. Training this number of adapters, first of all, the performance is considerably better than the GPT-4s. The efficiency in terms of compute is going to be far better to use these smaller models. Like we said with LoRAX, if you train a whole bunch of adapters and just swap them out using LoRAX, swapping them out has fairly negligible amounts of latency, but you're able to just use a very small GPU as opposed to hosting GPT-4 on a much larger one. You're able to just query these adapters very quickly using a much more lightweight solution.
Awesome. I'd also add too, when, open source versus commercial, you own your models, you own that IP. So always, if you're going to be using a open source model to train your own adapters, you get the ownership benefit too, which is pretty critical, right? Mm-hmm. Question for you guys. There was one fun one at the end that I think, Justin, you'll appreciate. Will you guys release a paper on your findings? We desperately need fine-tuning scaling laws.
Yeah, great question. We absolutely are working on a paper for all these results. I think a general rule of thumb in research engineering is that, if you're going to put in the effort to run a lot of experiments, you should try to get a paper out of it. So that's absolutely what we're trying to do. Yeah.
Awesome. If not, at the very least, we will have a blog too, right, on some of these findings. Someone noted, and we had talked about this internally, interesting that Mistral instruct and perform better on average than base Mistral. Any intuition on like why this occurred?
Yeah, so this was one of the stranger findings of the bake-off. Like out of the box without fine-tuning, the instruct model is better than the base model. But yeah, I think it kind of goes to show like the power of fine-tuning, that with the specialization step, the kind of the base model is able to be equal or better than instruct. But in terms of why instruct still doesn't, I would say the difference is pretty small overall. Yeah, the additional speculation I have is that the instruct model, it's actually using that kind of INST tagging protocol. I don't know if people have seen that, but that is not something that we have in our prompt, because we wanted to use the same prompt across the board. And so it's possible that the instruct model kind of is overfit to that. And so when it kind of starts learning from strings that don't have that tag, it has to kind of deal with kind of a higher level of loss, while the base model doesn't have those tags, or it wasn't trained with those tags. So it's kind of immediately able to start its gradient descent in a more efficient way. Yeah.
It's also interesting that we noted that difference, not just in Mistral, but also in the Gemma models as well. I think the Llama models were the only one where the instruction tuned model surpassed the vanilla model after fine tuning and performance. So just an interesting finding that was overall a little bit unusual for us.
Thanks for that. A lot of questions sort of about data set size, the steps, batch sizes. Maybe just a high level, someone sort of summed it up. Like, could you just elaborate a little bit more on like best practice or thoughts around your training data size, the steps and the batches, and how that comes to play with fine tuning?
Well, let's see. At Predibase, we try to abstract, a lot of the training parameter details from you as much as possible. We want to make sure it's a good experience. In terms of dataset size, like, I think Tim presented a table showing that, the 29 tasks, various sizes, various levels of different amounts of sequence lengths. And so, yeah, there's a lot that the Predibase platform supports. I would say if you're just getting started, and you have 30 million examples, take a subsample of that to down to 10,000 and see what fine tuning gets you there. 40,000 training steps, which is what we did. It was actually under an epoch for a lot of these data sets. And so you don't even necessarily need to go to a full epoch before you see that lift over GPT-4.
Great. And maybe one last question that I think is interesting that just popped up as we wrap up, and we'll try to answer these after the webinar too via email and what have you. But how important was the prompt template? When you think about fine tuning, do you need to do a lot of engineering on the prompt template, or not play a bigger role?
Yeah, I can maybe speak to this. In a lot of our earlier experiments, we did find the prompt that changing up the prompt template actually could provide a significant amount of lift. We did very early on, we did some experiments with tabular data to see if it could, to see what we could do with an LLM. And there, even just changing the order of instructions in a prompt could end up significantly impacting performance. So for us, we wanted to just make sure that we had very, very clear instructions to ensure fairness across our evaluations, as well as to just make sure that this LLM had the highest probability of outputting the exact format that we wanted, as well as producing high quality information.
I also want to add that one of the big benefits, I see this as actually one of the big benefits of fine tuning, which is when you're using these pre-trained models like GPT-4, there's a lot of prompt engineering that you might have to do. You have to add in examples, or you have to, reprompt it, or, majority do some ensembling thing to get the performance up. With fine tuning, you really can be very trivial about, or offhand about how you write the prompt, because the model is going to go through the supervised learning step. You can have a very short, very concise, minimal instructions type of prompt, and then the model is still going to get really good quality.
Awesome. You might even say the future is fine-tuned. I want to thank our speakers today for this awesome deep dive into all results and best practices and lessons learned. And thank you to everyone for joining us. A lot of great discussion in the chat. As a reminder, you can try Predibase for free. You can fine-tune and serve many of the popular open source LLMs on our platform. We'll give you $25 from free credits. The recording will be shared after as well. And if you have any other questions, jump in the free trial and ask our support team, and we'll be there to help you. But thanks again for joining, and thanks to our speakers. Take care, everyone.